So today we will learn about regression and regression theory. There will be a separate video for the doing of a regression. This is following in and kind of lumped with the correlation video and the correlation unit. Why? Because correlation and regression have a lot in common. They both describe that linear relationship and that concept of the linear relationship with the scatter plot and the dots converging upon a line. We discussed that already, and correlation and regression have that in common. Correlation and regression, the data looks exactly the same. The data entry looks exactly the same. You've got these two quantitative variables, one in each column, and each of those data points is collected from whatever your research participant is. It could be Taco Bell franchises, or it could be physician assistants. It could be anything, right? For example, we have, this is data from ages ago, or I could say there's a correlation between performance on exam 3 and exam 4 in this class. And that's my on-campus class. It's taught in a twice as long format, so that data doesn't apply to you guys. But again, it does show the idea that each of those little dots on the graph, each of those little green diamonds represents a student and their exam 3 and exam 4 grades. Again, correlation does not equal causation. Regression doesn't equal causation either, but it does allow us to make predictions. So that's why I have the crystal ball there. This is what makes regression special. And this is why there's money in statistics in regression. Regression lets you take information from the past and make a good bet about the future. So correlation just tells you about like the strength and the direction of a linear relationship. Regression goes a step further, and it does not have a crystal ball. It's math. Math is used to make predictions about the future. And again, that's why it can come in handy. And that's why stats jobs are booming right now. There's my mic. Because you can use past data to make predictions about the future, which is why regression is popular with psychologists, right? Psychology as a discipline wouldn't exist if there weren't patterns and behaviors, and we couldn't make predictions about human behavior in the future unless we had some data from the past. So I use the crystal ball tongue-in-cheek. There's no actual psychic powers involved. At least the way I do regression, there isn't. Maybe you're special. It just means that we can use past information to make predictions about the future. And it all has to do with the line, a regression line. And that's another important piece for distinguishing between correlation and regression. So how do we distinguish? Regression is used to make predictions. How do we use those predictions and make those predictions? Via math, and that math is defined by a line. Do you guys remember back in the day, maybe elementary school, maybe junior high school is probably introduced at different times, when your teacher would bust out the graph paper and like you draw like your two axes, right? And she'd give you coordinates and you draw, and then you'd give other coordinates and rise over run. Is that a little familiar? That's still the linear regression equation. We're talking about a slope and a y-intercept in order to define a line. And that line is going to fit our data, which is a separate but related concept I'll get to in just a moment. So, put over here. So what do we do with regression? Again, you've done this before. This idea of rise over run. And this is from mathisfun.com, which we talked about with the normal curve. So again, remember the idea that you have this regression line and you can change the slope around, right? And you can change your y-intercept around. Oh, excuse me, that's the slope and this is the y-intercept. And you can change the line and define a line. That's what we're dealing with. Our linear regression now is featured right here. Linear regression. It's y equals a plus bx. And again, this is all open book, open note. It maybe doesn't behoove you to memorize the formula itself. You'll have access to this for the homework and the exams, but you need to know the parts of it. And you need to know the pieces of this formula. So what is this formula? Okay, so first we have x and y. That's cool, right? X and Y variables. That's referring to the data that's graphed on the X and Y axis. So these are your two quantitative variables fitting into the equation. That's kind of familiar, but you also have this A and the B. What are A and B? A is known as the regression coefficient, but also the y-intercept. So literally, if you have your X and your Y axis and you have this line, where it intercepts the y-axis, that number on the y-axis is A. And then you still have, oh, this got kind of screwed up, sorry. And B is the regression constant, which is your slope. So if you have this line that you use to make your predictions, and that line is defined by all of your data points, the slantiness, if you will, of that line is the slope. We call that B. So again, X is your X variable, Y is your Y variable, A is your y-intercept, B is the slope. And can we just take a quick moment to look at this equation? You have a bunch of noise over here on the right side of the equation, and you do all this math, and then it equals Y. So, and this is an important point that I'll make a few times. When you're doing a correlation, even when you're doing it right in JASP, X and Y data points don't matter. You're just looking for the linear relationship. It doesn't matter what you define as X and Y. It matters a lot in regression. This is another way regression and correlation are different. In regression, while it's not causal, mathematically, you're stating if you take your X variable, multiply it by the slope, and add the y-intercept, you're going to have your best bet for Y. So you're using X to predict Y. Mathematically, it's very specific, right? You can see the equation there. So X is used to predict Y. How? Via this regression line. I'll jump to it in a moment, but do note that that regression line is created for you by JASP, and JASP finds the best fitting line. So this is information that you'll extract out of your JASP output. And I really hope by this point in the semester, you're feeling okay about JASP. You've used it often enough. I know that I'm asking you to do different processes in JASP, but hopefully you're starting to appreciate that it's pretty straightforward point and click software. Go over there, HeartNet. There we go. Okay. So I'm going to reiterate that X and Y matter. So variables in regression, again, in correlation, X and Y, that would just denote which axis it's on. But now X and Y matter. So X is kind of like your independent variable, the manipulated variable used to predict your outcome variable, your dependent variable, or Y. So sometimes the independent variable is called a predictor, and the Y variable is called the criterion, which I don't think are very helpful terms. I prefer to think about it just X and Y because it translates directly to the equation when I think about it. So what do I mean by this? Let's say you can conduct an experiment to test whether or not the number of hours a participant sleeps, variable X, can predict, that's the regression language, can predict how long it takes a participant to run 1 mile, which is your outcome variable. This is just BS data, right? We're just saying maybe physical fitness is contingent in some way upon your sleep quality. Again, totally made up. Please don't go to any of your professors and tell them that I told you this. But what would the data look like here? I would put in the number of hours you slept. Maybe you only got 5 or 6. Maybe it's the long weekend. You got a nice 10 hours. That'd be amazing. 10. And then what would I do with all of my data? So I'd have all of this data. I'd have like 100 participants and I'd say, how many hours did you sleep last night? Okay, now I've got my stopwatch. Go run a mile, right? That would be what my data collection would look like. There'd probably be an informed consent in there somewhere. But that's what the data collection would look like. And what would I have to look at? I would take, once I had all of that data gathered, I could then have a new participant come in. And I'd say, okay, how many hours did you sleep last night? And I'd put that to my equation. I'd multiply it by the slope from that 100 participant data, that scatter plot and the line I'd create. I'd add the y-intercept for the linear equation that I created out of my 100 participant data set. And then I could predict the hours how long it took you to run. And to be clear, this is just a little experimental setup, but you can also see if you could make a prediction of like, how much money in US dollars did your firm spend on Facebook ads? And how does that predict sales? If there's some atmospheric condition that I can measure and I can use that to predict inches of snow, that would be worthwhile. That would be a more accurate weather forecast. So I might use silly examples or random examples, but I want you to kind of think about, oh, this would have real world implications if I could use some variable to predict something that would make people money, make people safer, allow people to recover from shoulder surgery faster. Just so you're kind of seeing the bigger picture there. And there be the regression formula. I know I keep on mentioning it, and I know it's an open book, open note test, but I'm just trying to present the information to you as clearly as possible. And I'm repeating it because this regression line's an important feature of regression. What is the null hypothesis in regression? X doesn't predict Y very well. You do get a p-value for regression, and regression has effect size, which we'll talk about shortly. What's the alternative hypothesis? X does predict Y. And I know I'm doing this a lot this morning, but to contrast it further, remember, with correlation, you would just say X and Y co-occur. What do you say in regression? Mathematically, X can predict Y, and I need to say it again. That does not mean X is causing Y. Doesn't mean X causes Y whatsoever, but it means that the two mathematically, you can use one to predict the other. Again, how would this look? How would this look if you made an actual prediction? This is from a textbook I used to use. Looking at the predictor and criterion variables, let's say I'm an admission counselor at Gannon, and I want to streamline the acceptance process, and I want to make sure that we are accepting students that can succeed at Gannon. So let's say I have your SAT scores, pretend they're GRE scores, right? And that's my X variable, and I want to use it to predict college GPA. So why would I do this? I would like to be able to predict which students are going to have the minimum GPA to get through Gannon, or I could even be more fine-tuned, and if different majors have different GPA requirements, I could dig my data down and separate my participants and figure that out as well. So here I am with a big pile of data, 10 years worth of data, and I have all of your SAT scores, and I've got all of your graduate GPA, like your final cumulative grade point average, right? So what would it look like? Maybe I have 10 years worth of data and I run my regression analysis on JASP, and this is what I get for my equation. So my Y variable is going to equal 0.3, big head's in the way. My head's actually very large in real life, not just for this video. So it's 0.3 plus 0.004 times X. To make it a little clearer, let's put my data variable names into this equation. My predicted GPA, because remember, that's the outcome variable. It kind of makes sense. That's like the big enchilada that you would want to know. That's the golden egg, the golden tick. I'm using a lot of metaphors. That would be the outcome variable of interest, right? So I would know your SAT scores. You applied to Gannon last year of college, right? And I'd multiply it by my slope, which is 0.004, my slope. And then I'd add 0.3, which is my y-intercept, which you can kind of see here. This is the regression line graphed out. And that looks like a 0.3 to me, doesn't it, right? So what would this look like when I try to use this for prediction? Okay, so I have these little questions for you. What is the predicted GPA for an SAT score of 721? Okay, well, let me put this somewhere reasonable. Okay, so if I'm trying to predict GPA based on an SAT score of 721, I would take 721, and I'd multiply it by my slope of 0.004, just to make sure I have this all right. And that would be 2.884, and then I would add 0.3. So if you had an SAT score of 721, I predict that you'd have a little scooch over a B, a little over B, nothing to be ashamed of, the 3.18. So this is the prediction piece. I'm sorry, I don't have a flashy crystal ball to show you. It's just math, but this is math being used to make a prediction. Again, with this, let's say I have an SAT score of 412. I take my 412 and I would multiply it by my slope of 0.004. And that gives you 1.648. It's not looking so great, but that kind of goes along with that regression line, right? There seems to be a relationship such that as GPA goes up, SAT score is going up. And then I would add my 0.3. So that's not so hot. That's not terrible by any stretch. That's almost a 2. You need to really clean it up, right? But that would be the predicted GPA. So what did Dr. Hartnett just do here? She got out her calculator and she did multiplication and addition. That's as bad as the math is getting here. All right, so the math isn't bad, but you need to know what this means. And again, what is this? This is the regression line. This line fits the data. We'll get there and explain that. And this regression equation allows you to make predictions. I'm talking about things, well, actually, this would be a high stakes prediction. I cannot spend so much money to recruit you guys, and we have student support staff and the whole rigmarole. Wouldn't it be nice if Gannon could better invest all of that money by targeting students with certain SAT scores? And yes, the SAT, I don't know if you knew this, but they sell your scores to universities so that they can then send you mailings. The dark underbelly of higher ed. So again, this would be high stakes, this sort of information. And if you could find the golden ticket, just one metaphor this time, that would allow you to make a really good prediction. This is where the money comes from. And also, this isn't like a pure stats job that I'd be talking about. It's like you're interested in college admissions and you can do a little bit of statistics. So I just hope you don't, I'm sorry, I'm getting sentimental because it's the end of the semester. I hope you're starting to see how this content would apply to situations other than this weird winter semester at this weird point in history. So here's another example. Let's say you can predict dragon weight from dragon height. So you've got all these dragons and you have all of these dragons. You're a dragon scientist, it's pretend, and you collect their height in feet and their weight in tons with data from hundreds of dragons. And let's say that this is the equation that you end up getting. This is from my friend Allison Hurst. I met her on Twitter. She's really good at cartoons and at stats. I'm jealous of her, but I also admire her. So this is what the equation comes from, right? So you collect all this data, you go to all the zoos and the dragon parks and out in forests, and you find all these dragons, get their height and weight. And this is the equation. So what are we saying with this equation? Moving forward, if I know that a dragon has the height of 10 feet, I could go 10 times 0.3 plus 2.4, and then I'd make my prediction about weight. I'm sorry, there's 100 examples. In my experience, you don't need 100 examples, you just need the one that clicks, and the one that clicks isn't necessarily the first one you see. So how can we use regression? We can use regression to look for patterns, like uncovering funding inconsistencies for gun violence research. And this is of particular interest to psychologists because of the trauma and the psychological services needed in the wake of gun violence. Also, if it's of interest to psychologists because with older adults, if you just look at people over the age of 18, 50% of gun deaths are suicide. So it would behoove us, call me naive, but I think that like if we have money and a government, we should use it to solve big problems that not one individual could figure out. And what's one way that the federal government helps out citizens and solves problems? By awarding grants so that we can have scientists in the field working off at their university, work on the problem without having to like swell up the number of federal employees we have, right? So instead of like having billions and billions of federal employees, instead we send money to researchers that work at other firms to solve problems. So on our y-axis here, I have funding in US dollars and billions of dollars. And on the x-axis here, we have mortality rate per 100,000 in the population. So this is a measure of how people die. So what are they trying to understand? Death is inevitable, but how can we prolong life and quality of life by better understanding the things that typically kill Americans? There's no sunny way of saying this. So what do we have? We have a linear relationship that kind of makes sense. Hernias kill fewer people and they get less funding. Cancer and heart disease kill more people and they get more research funding. Reasonably so. Peptic ulcers, penetrating wounds, bile tract diseases, fires. Again, you see this linear relationship in the scatter plot, right? Such that the more people die of a given disease, the more funding's going into it. And you do see some outliers. HIV is kind of up there. It's killing this many people, but it's receiving an amount of funding typical of cancer, heart disease, diabetes. It's also interesting with some of these like diabetes. I wonder if this wouldn't be necessarily the cause of death for some people, but it would contribute over time to the injuries to a body. And you also see some outliers down here. So these are things that maybe they're kind of worried you can't really treat with science, like drownings and falls, accidents. Our ability to affect that is maybe more difficult, and gun violence is down here as well. So what did they do with this regression equation? They looked at mortality rates and funding with the idea that we should give more money to better understand things that are killing a lot of Americans. And gun violence is all the way down here. So for this amount of death, it should be up here around liver disease, sepsis, motor vehicle, right? It should be up here, and it's not. They got their regression equation out of this. Who's they? This was published by the Journal of the American Medical Association. You can see more here. Gun violence had 1.6% of the funding predicted, given the number of people that die that way. So if we were just looking at this overall trend, and if gun violence funding followed this trend, you would have expected $22 million in research. I'm sorry, excuse me, you would have expected $1.4 billion in research. That's what they predicted, but instead it was only $22 million. And this down here kind of reflects a lot on this. What do we see down here? These are publications. So why measure publications? If we're doing science to save lives, how is science shared? Through scientific publications. So we're not just talking about the newspaper or your favorite author, we're talking about scientific publications. Again, you see the strong linear relationship. Cancer kills a lot of people, and there's a lot of publications about cancer. Same with heart disease. Penetrating wounds and fires kill fewer people, fewer articles. Gun violence, again, is the outlier. Why is this? The Dickey Amendment to, I believe it was the 1995 US budget, said that the federal government could provide funding to research that might result in a recommendation for gun control measures of any sort. So I'm not talking about taking away your guns. I'm talking about maybe mandated locks, mandated background checks, things like that. And just before you tell your parents I'm your Marxist professor, I grew up in Blair County, Pennsylvania. I've been to the shooting range. I know a lot of very responsible gun owners. But I just wonder if we could make even more responsible gun owners, if we could make even more safety in gun ownership, if we better understood gun violence, if we understood death by suicide related to using a firearm, and if we could make the world a safer place. Okay. So up until this point, I've been talking about the fit of the data, the data that fits the line. We're going to talk about that and how you find the line that fits the data, which then results in that equation that can be used to make predictions. So I present to you from a former textbook, 4 lines. Okay, so it's a little busy up here, but look at the blue dots on this graph. So this is used for X hours slept to predict Y happy mood. And what do we see here? Don't sleep, this is pretend data, but it kind of intuitive. Don't sleep a whole lot, low mood, sleep a whole lot. You're ready for your day, right? And these different rules, 1, 2, 3, and 4 represent different lines. So this is rule 2, like that looks like a lousy line to fit this data, right? It's for educational purposes, as does rule 1. Rule 1 and rule 2, they look terrible, but rule 3 and rule 4, which line better fits the data? Which line would lead to an equation that mathematically would be more likely to make more good predictions? All right, you don't need to do this by hand. You don't need to memorize this process. You just need to listen and have a reasonable understanding of the process. So what do we start out with? Hours slept, our X data, and our actual mood. And then what does JASP do in the background to find the best line? It tests a bunch of lines. So here's rule 1. And this, remember, rule 1 is this wonk line, right? But this is the equation for that line. Rule 2, this is the equation for that line. Remember, 1 and 2 were terrible. Rule 3 and 4, good contenders. So we have rule 3 and 4 here. So what do? We have actual Y. Then look, all these little Y's with little boop hats on. Y hat, Y caret, whatever you want to call it, is the way we say a predicted Y. So Y is actual Y. Y hat is the Y that would be predicted via the equation. So if I take 5, and if I input it in X here, multiply it by 0.18, and then take 8 minus that value, remember, I would get a Y value of 7.1. Remember, that's the garbage line. The actual mood was 2. The predicted mood was 7.1. That's a terrible prediction. That's bad news. Rule 2, not quite as terrible, but still not great, right? If I took 5 and I put that in, multiplied it by 0, added 4, these are all 4 because you see here that the slope is 0 because the slope was flat, if you'll recall. Not great, but what happens with these two? If my actual mood is 2 and I'm getting a 2.5 and a 2 for my predictions, that's not terrible. 2 is awesome, but that's just 1 point. So what do? For every single X, you input it to get the predicted Y, right? But you're not done yet because you take this data and you use it to basically figure out how different is the actual data from the data predicted for a particular line. Boop. All right, so this breaks it down. Instead of having 1 through 4, now we have 1 and 4. So this is that predicted data for rule 1, which remember, it's terrible. Predicted 2, got 7.10 to go down the list. Predicted 4, got 6.74. You would find the error associated with your rule, which is actual Y minus predicted Y. Bunch of positive and negative. So if we just add this together to get some grand total of the amount of error, positive and negative numbers are going to cancel each other out. So what do? You square them all and you add them together. And then you do that again for rule 4. Remember, rule 4 was a contender. So look at that error rate. If a 0 means perfect prediction, and then you square it to get rid of your positives and negatives. And what do you have for rule 4? Your error is 6. The sigma sign is the summed error. You want that value to be low. This process is known as the least squared error principle. What are these least squared errors? You take the error, which is Y minus Y caret, you square it, and then you look for the one that's the smallest, least squared error. SPSS does this for us. That's a lie. Sorry, I should say JASP does that for us. So you get a line that fits your data. How do you evaluate this line? How do you evaluate how well X predicts Y? This is a comic from KCDX, which is a really funny, nerd funny webcomic. I don't trust linear regressions when it's harder to guess the direction of the correlation from the scatter plot than to find a new constellation in it. So I warn you now, any old scatter plot can give you a regression line. JASP will spit out a regression line for anything. It doesn't mean it predicts well. You do get a p-value as well. There's some other values that we use to discuss the worth, if you will. By worth, I mean the ability to predict of any given regression line. This is a joke from Twitter, nerd funny. So Chris Madison says, sometimes it's hard to see a data plot and believe that the stats were done appropriately. And you can kind of squint and see the scatter plot where they found a regression line in this data and it didn't look that great. And then someone else claimed to find the regression line and they wrote nope as the regression line because this looks like a big random distribution of data and this red line doesn't really seem to predict it very well. Stats joke. So one way to evaluate your regression is via p-value, but also r-squared, which is like an effect size. R-squared is indeed just your correlational coefficient, the Pearson's correlation coefficient squared, known as shared variance. How much variability in Y is explained by X? So what is variability? Variability is all of the different answers. So if I ask you all for your resting pulse rate, I'm going to get different responses. That's variability in my data set. But where does the variability come from and how much of it is shared between the two variables such that the two variables have some sort of correlation, have some sort of regression ability? So my example from before, maybe all of the variance in hours slept is 100% of the variance. And all of the variance in running times is the share 100% of the variance. And then remember your old Venn diagrams from outside this class, that overlapping circle is like r-squared. Our psychologist, Christopher Magnuson, of whom I am a fan, we looked at this one before. We're going to expand upon this. So we looked at this before just to talk about the scatter plot, but now we're talking about all this shiz over here. So this is the shared variance. Shared variance is indeed, it's not just my idea, it's visualized via a Venn diagram. So let's say I have a correlation of 0.57. If you square R, you get the shared variance, or R squared, of 32%. That's what 32% overlap looks like, which means the shared variance. How much of the altering and the changes in variable X are altering and changing variable Y? And you can even see down here, to a greater extent, they even show you what the regression equation would look like for this particular line. Means and standard deviations aren't very helpful when you're talking about covariance. But again, you can kind of see here, as well as a review, you can see how the slope and the y-intercept are changing in my data as well. So again, shared variance, Venn diagram, shared variance, R squared. How much of the variability in y is explained by X? Yes, it is just a Venn diagram, right? And the overlapping piece is what you're looking out for. B is slope. Beta is the slope, but it has been standardized. And beta here, you can see that's big old capitalized Greek letter beta. When you're doing your write-ups, you can just type in beta. I don't expect you to like look through Microsoft Word for Greek letter beta unless you want to. If you're fancy like that, go ahead. The beta coefficient is the degree of change in the outcome variable y for every 1 unit change in X. So for every 1 unit change in foot size, there's a 0.9 unit change in shoe size. This would be a near predictive relationship. So that would mean that the beta would be 0.9 there. Perhaps for every 1 unit change in hour sleeps, there's a 0.09 unit change in time for a mile run. That would be a really weak relationship, right? If every time your hours slept, only 0.9 of the units of running time slept, that wouldn't be very impressive. There wouldn't seem to be much of a relationship. So beta is standardized. It's on a scale of 0 to 1. The closer to the 1, the more y will change based on X. Closer to 0, the less it changes. Why would you do this? It's standardization. Remember standard deviation from back in the day, all the way back in 2020, accursed 2020. Standardization provides instant contact. Instead of talking about the scale of measurement you started with your study, now it's all scaled from 0 to 1. Your beta will be 0 to 1. It's interpreted like any old effect size. Closer to the 1, the more change in X can be, or change in Y can be predicted from X. Closer to 0, the less change. And we will do the regression example in the next video.